Hi everyone, this is Mrs. G, and today we're going to be using probability to talk about fair decisions, fair games, and how to analyze decisions. All right, I have a quick warm-up for you guys, so go ahead and pause the video and give it a try. All right, go ahead and check your work here. So first thing to notice is that the area of the total target, it's a 6 by 6 square, so it's 36 units squared. Then to find the probability that it will land on these different colors from the target, you simply find the area of those different spaces. So for red, we just do pi r squared with a radius of 1, so simply pi. So it's pi over 36, which is the total area, so a probability of 0.09. Find the area of blue, just be careful. The radius of the entire circle is 2, but again, we just want this ring, so we have to subtract away the red. So the area is 3 pi, so 3 pi over 36. And then for yellow or red, so remember we're going to do the probability of the yellow plus the probability of the red. So we have probability of the red from above. And then for yellow, again, the radius is 3, but we have to take away the red and the blue, so the area is 5 pi. So 5 pi over 36 plus pi over 36 would give us our probability. And then the area not within the circle, or it is the gray area, so I did 36 minus the entire circle, which would just be a circle with a radius of 3. Now this entire thing is our area. I know it seems kind of weird, but the area is 36 minus 9 pi. So you do all of that divided by your total area to give you a probability of 0.21. All right, so again, today we're going to be talking about this concept of something being fair and making fair decisions. So first of all, what makes something fair mathematically? And that is when each outcome has an equal probability of happening. So a couple really basic examples, let's consider like a raffle ticket. So if each person gets one raffle ticket and then you randomly pick one from the box and the winner gets that prize, is this fair? So in this case, since all of the raffle tickets are just in a box and you're randomly picking one from the box, each ticket has an equal probability of getting picked. So each ticket has equal probability of getting picked. So since this is true, we would call this a fair scenario. This is a fair method of awarding that prize. Now let's look at another raffle example, but a little different. In this case, each raffle ticket costs $5. And you can buy as many as you want, but then again, at the end, one is randomly picked from the box and the winner gets that prize. So is this also fair? So maybe you're thinking, well, this isn't fair because, if you buy more tickets, then the odds that you win are greater. However, again, we just need to look at the actual event that is picking the winner. The event that is picking the winner is one is randomly picked from a box. So for each ticket, you still have an equal probability that it will get picked. So regardless of the fact that some people may have bought one ticket, some people may have bought 3 or 10, again, each ticket has the same probability of getting picked. So this is still considered fair. So this is fair, but also a way to incentivize people spending more money. But again, it doesn't exactly penalize someone that only bought one ticket, because again, that one ticket has the same chance as any other person's individual ticket. So each individual ticket still has equal probability of getting picked. So again, kind of different scenario, but still considered fair. All right, so now let's talk about another way to solve problems fairly, and that's a common way of doing this is with what's called a random number generator, which your calculators can actually do. So a random number generator, you tell it which range of numbers to pick from, and it will randomly select as many numbers as you want. So here you have a class of 24 students that sold 65 magazine subscriptions. So you could see right off the bat that there's not an equal number of sales for each student because 24 doesn't go into 65 evenly. So maybe some kids sold 1, maybe some sold 5 or 10, and maybe some sold none. So the teacher wants to incentivize students to sell subscriptions, so she wants to award a prize, but she wants to do it in a fair way. So how can we award a prize in a fair way, but also, incentivizes you selling more, right? We don't want to say that if you sell 10, it's the same as selling 1, but we still want it to be mathematically fair. So for something like this, what you could do is you could take the numbers 1 through 65, which would represent how many are sold. So that's the number of magazines that were sold. And then imagine you take each of those numbers and you write them on a slip of paper. So each student gets one number for each magazine they sold. So each student gets one number for each magazine sold. So if you sold 1 magazine, you just get 1 number. If you sold 5 magazines, you get 5 numbers. And then at the end of the fundraiser, you would use a random number generator, which your graphing calculators can do, to pick a number from 1 to 65. So the idea here is that although some students may have more than 1 number because, again, they sold more than 1 magazine, each number has the same probability of getting picked from the random number generator, so we would still consider this to be a fair way of giving out the prize. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, so here's one way we could do this in a fair way with the random number generator. So again, since there were 20 total coats that they donated, you could take the numbers 1 through 20 and again write them on slips, and then give different people different amounts of numbers based on how many coats they collected. So Jacob collected the most coats, so he got the most numbers, and then Ben gets 6 numbers, and then Ryan and Zach each get 3. So although, Jacob has more numbers than anyone else, at the end you use a random number generator to select 2 of the numbers. So each individual number has the equal probability of getting picked. So we would still consider this to be fair, while also awarding Jacob for collecting the most and Ben for collecting the next most. So it's fair mathematically, and it incentivizes you to donate more coats. All right, now we're going to look at another really interesting scenario. So this general concept is called the problem of points. So consider this scenario. So 2 students, Rosemary and Catherine, find a box containing 100 Pokemon cards. To decide who gets the cards, they come up with this game. So one student starts flipping a coin repeatedly, and every time it lands on heads, Rosemary gets 1 point. Every time it lands on tails, Catherine gets 1 point. And the first one to get 20 points total gets all of the cards. So it's an all or nothing game. But let's say Rosemary and Catherine are playing, but they get interrupted. So how should you fairly divvy up the 100 Pokemon cards if the current score when that game gets interrupted is that Rosemary has 19 points and Catherine has 17? So maybe like your initial thought is to say, well, Rosemary is closest, so let's have her get all of the cards. But we know that although Rosemary is closer, Catherine still has a chance of winning. So we really need to look at kind of the different pathways of what could happen for the remainder of this game, and then decide from there how to divvy up the cards. So if you look, since Catherine has 17 points, that means that, and Rosemary is 19, that means that at most 3 coin tosses would be needed to finish the game. So we would need to do at most 3 more tosses. So now let's assume we're doing 3 tosses. We want to look at all of the possible outcomes for 3 tosses. So we know that we could find the total outcomes here, just, because each toss there's 2 possible options. So we can do 2 cubed. So there's 8 possible outcomes. We want to look at those and we want to see which ones would result in who winning. So the 3, there's some different combinations that we could get. We could get 0 tails and 3 heads. We could get 1 tail and 2 heads. You could get 2 tails and 1 head, or you could get 3 tails and 0 heads. So within each of these, we could figure out how many different combinations there are. So we could just list these out. It wouldn't take us very long to do because there's not that many combinations, or we could use our combination formula. So for all of these, let's consider heads to be favorable outcomes. So for the first one, we have 3 flips, and we're saying what if all 3 are heads? Well, there's one way to do this. Here, again, there's 3 flips, and we want to know how many ways can 2 of them be heads. And if you do 3, choose 2, that's 3. Here, 3, choose 1, so 1 favorable outcome, that's also 3. And then here, how many ways can we get 0 heads? It'd be 3, choose 0, which is 1. Okay, so you can see here that there are 8 possible combinations for these, for tossing 3 coins, or tossing a coin 3 times. So now we want to look at these and we want to decide which one of these, let's pick Rosemary, which one of these outcomes, or how many of these outcomes would result in Rosemary winning. So Rosemary just needs 1 more head to win. So she would win in this scenario, and all of these scenarios, right? And then for Catherine winning, Catherine would only win if she got all 3 tails. So there's only one way that Catherine could win. So if you look at those individual probabilities, so the probability that Rosemary would win, so I'll say R for Rosemary, well, there's 7 favorable outcomes out of 8 total. Remember, we did 2 times 2 times 2. Or if you add all of these up, that's the total number of outcomes. So the probability that Rosemary would win the rest of this game is 7 out of 8. And the probability that Catherine would win is simply 1 out of 8. So since we know the probability that they would win the game, we can take that and we can multiply it by the number of cards that we have to determine what percentage of the cards they should get. So this is essentially saying that Rosemary should get 7/8 of the cards, and Catherine should get 1/8 of the cards. Now from here, if Rosemary would get 7/8 of the cards, that would mean that she gets 87.5 cards, so 7/8 of 100, and that would mean that Catherine would get 12.5 cards. So of course we don't really want to cut a card in half because that would, essentially make the card not valuable anymore. So maybe we give Rosemary 87, we give Catherine 12, and then maybe for that last card they do something fair, so maybe they flip a coin again to help them decide who gets that last card, because again, a coin flip, there's a 50-50 chance the probability that either of them win is the same. So that would be a fair way to decide who gets that last card. So we'll say here's Rosemary, here's Catherine, and we'll say coin flip for last card. There you go. So again, when you have a scenario like this, we can consider the probability that one or the other person would win and then use those probabilities as a way to divide up the cards instead of just giving all of the cards to whoever is closer, because again, we're not taking into account the fact that Catherine still could have won this game even though Rosemary is ahead. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So if Rosemary has 18 points and Catherine has 16, there's a possibility that they could have up to 5 more tosses before the game ends. So one way to think about this is Rosemary could get 1 more point and Catherine could get 3 more points, and it'd be tied at 19-19. So the game would still be going, but in that next toss, the game will certainly end because one or the other will win. So if you add those up, that gives you 5. So there's 32 possibilities in terms of outcomes. And then for the breakdown of the different combinations from 5 heads and 0 tails all the way to 0 heads and 5 tails, you just use these combinations. The ones highlighted in blue result in Rosemary winning because she only needs 2 more heads to win, and the ones in red result in Catherine winning. So Rosemary has a probability of 26 out of 32 of winning. Catherine's probability is 6 out of 32, so you can multiply those by 100 to see how to divvy up the remaining cards. All right, so now we're going to move on to this concept of fair games, and that ties into this idea of expected value. So let's look at a scenario. So you are playing a game where you flip a coin 3 times. If you flip heads, 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 or tails, 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 you get $10. But if you flip anything else, you get nothing. So if it costs you $3 to play this game, is this a fair game? So to determine if something is a fair game, we need to know the expected value of playing this game. So that will definitely involve us finding the probability of the different outcomes of this game. So first of all, if you're flipping a coin 3 times and each flip there's 2 possible outcomes, there's 8 total outcomes in this game. Now there's 1 outcome, so there's 1 way that you can get heads, 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 and that's by getting heads, heads, heads. So the probability of getting all heads, the probability of this, I'll say this, is 1 out of 8. The probability of getting tails, tails, tails is 1/8. So that means the probability of getting anything else, I'll say other, is 6 out of 8. So now that we know the probabilities of the things that matter, so the 3 things that matter are all heads, all tails, or anything else. Now that we know those individual probabilities, we can find the expected value of this game. And we do that by essentially taking the probability of each thing and multiplying it by the reward that you get. So for this thing that has a probability of 1/8, you would win $10. So the expected value from just this is 10 out of 8. This one you win $10, so 10 out of 8. And then this one you win $0, so you get the expected value from this is 0 out of 8. So then the last thing we need to do is simply add up these 2 expected values. So 10 out of 8 plus 10 out of 8 is 20 out of 8. And again, by expected value, we would say how much money would you expect to make from this? So then if you do 20 divided by 8, that gives us 2.5. So the expected value of this game is $2.50. So based on the probability of these different things happening, the expected value of the game is $2.50, but it costs us $3 to play. So since they're charging more than the expected value, we would say that this game is not fair. So again, we need to consider the individual outcomes and then how much you earn from those different outcomes happening. And then you essentially add up all of those individual values to find the expected value of the game. All right, so now I'm going to have you guys try one on your own. So pause the video and give this one a shot. All right, go ahead and check. So in this case, there are 8 possible outcomes, but here we have to find the probability that you get exactly 2 heads. So this probability would be 3 choose 2 over 8, so it's 3 over 8. So remember, we do 3 choose 2 because, again, it's a combination. It doesn't matter which flip gets which outcome, but you're just saying how many ways can I take 3 coins and 2 of them are heads. So it ends up being 3 over 8. Then we multiply that probability by the amount we would win, and we get 48 over 8, which is 6. And then here I have the probability that it's not 2 heads, so the complement is 5 or 8, but we get $0 for that, so the expected value of that event is 0. So you add up the 2 values and you get the overall expected value, which is $6. So since that is equal to the cost to play this game, we would say this is a fair game. All right, so let's try another one together. This one says, in a game, you pick a card randomly from a standard deck. If you pick a 2, you win $2. If you pick a 3, you win $3. And this pattern continues through 10. So if you pick a 10, you get $10. And then if you pick an ace, you win $11. Now the face cards win you nothing. So what should be the price to play this game to make it a fair game? So they're essentially asking what is expected value of this game. Okay, so let's look at all of the individual probabilities here. So the probability that you pick a 2, well, they're all going to be 4 out of 52 because there's 4 of each type of card. So the probability you pick a 3 is 4 out of 52. The probability you pick a 4, 4 out of 52. So we're going to continue this pattern on for all of them. Out of 52. And we just have a few more. Okay, and then remember the probability that you pick an ace is still 4 out of 52. Okay, and then for each one, each of these different events, there's a different payout. So for this first one, we're going to multiply it by 2 because you win $2. Here we win 3, 4, 5, 6, 7, 8, 9, 10, and $11. And then remember for the face cards, you win none. So the probability, you could write it out and then multiply it by 0, but since you're not winning anything for those, we just don't even need to include it. So then from here, we're essentially going to go in and add all of these up. So for the expected value, we're going to add up those individual payouts based on their probability. So it's for our numerators, it's 8 plus 12 plus 16 plus 20 plus 24 plus 28 plus 32 plus 36. Let me zoom out just a little. Plus 40 plus 44, all over 52. So the expected value of this game should end up being exactly $5. So that's how much you should charge for this game if you want to make it a fair game. All right, so again, I have one for you to try on your own. So please pause the video and hit play when you're ready to check. All right, go ahead and check your work here. So the probability that you pick a red card that is an ace through 10, so ace and then 2 through 10, is 20 out of 52, and you win $10 for any of those events. And then the probability that you pull a red card that's a face card is 6 out of 52, and those you win $25. So if you add up those two individual amounts, you end up with $6.73. So in this case, you should definitely play because the expected value is actually greater than the cost to play. All right, so now we're going to start talking about how we can analyze decisions using probability. So here we have a case where scientists have developed a test that can be used at birth to determine whether a baby is right or left-handed. The test has been developed long enough for scientists to track the babies to see if their test was actually accurate. So the test was used on 1 million babies. About 10% of those babies actually turned out to be left-handed. The scientists learned that when the children are left-handed, the test correctly identifies them as left-handed 92% of the time. And when the children are right-handed, the test correctly identifies them as right-handed 95% of the time. Is this a good test of left-handedness and right-handedness? So at first glance, you might see these two numbers. You say, oh, well, it works 92% of the time for left-handed and 95% of the time for right-handed. This is pretty good. But you need to look at the context of those percentages. So here, one way we can kind of break it down a little more is by filling out a two-way table of data. So there are 1 million babies or children in this study. And as it says right here, about 10% of babies actually turn out to be left-handed. So if you look at these two rows, actually left-handed, this would be 10% of 1 million, so 100,000, which means that 900,000 babies turn out to actually be right-handed. So then this says, this next piece of information is actually a conditional probability. It says that when the children are left-handed, the test correctly identifies them 92% of the time. So you're setting the condition that they actually are left-handed, and then you have to find 92% of that. So 92% of that would be 92,000. And again, that's showing the of the babies that are actually left-handed, how many actually tested left-handed. So work for 92,000 of them. But then that also means that for 8,000, they are actually left-handed, but they tested right-handed. Now, if you look at this next piece of data here, I'll highlight it in green, when the children are right-handed, so that's the condition here, so we'll only be looking at this population of the study. The test correctly identifies them as right-handed 95% of the time. So we have to find 95% of 900,000. So 95% of 900,000 is 855,000. So again, that's of the babies that test or that are actually right-handed, 95% of them test right-handed, but then that means that the rest of them, so 45,000 that are actually right-handed, test left-handed. And then if you add up the columns here, we have information about how many babies test left-handed, and that'd be 137,000. And this would be 863,000. So now that we've been able to use those statistics provided to give us a kind of a more broad picture of what's going on, now we can tackle this question of, is this a good test of left or right-handedness? So essentially what I would like to know as a parent is, if my baby takes a test and they test left-handed, what's the chance that they are actually left-handed? Or if I take the test and they test right-handed, what is the chance that they are actually right-handed? So I want to know, how accurate are the results? So to find that, we can find two different conditional probabilities. So again, I want to know if the condition is that my kid actually tested left-handed, what's the chance that they actually are left-handed? So the probability that they're actually left-handed given that they test left-handed, because that's how you can actually figure out if the test is accurate. And then we would also want to know the probability that they are actually right-handed given that they test right-handed. So if I give my kid the test and it says they're right-handed, what is the probability that they actually are right-handed? So for this first conditional probability, again, the condition is that they test left-handed, so that would be this many toddlers in the survey, and then 92,000 of them are actually left-handed. And then for this one, the condition is that they test right-handed, so 863,000. How many of them are actually right-handed? So 855,000. And let's get some decimals for those. So for this first one, you get about 0.67. So if this, to interpret what this means, it says if your baby actually takes the test and it says they're left-handed, there's only a 67% chance that they are actually left-handed. So I would say that this test is actually not a very good indicator of left-handedness. Again, only about 2/3 of the kids that actually say they're left-handed end up being left-handed. But now let's look at the right-handed. So if you plug this in, you get about 0.99. So this is 99% accurate. So this says if your kid takes a test and it says that they're right-handed, there's a 99% chance that they actually are right-handed. So I'd say if you take this test and it says your kid is right-handed, you can probably assume that they're right-handed. But if it takes the test and it says that they're left-handed, I wouldn't take that as a fact. So I think it's a good test for right-handedness, but I would not call it a good test for left-handedness. So again, the way that statistics are presented can sometimes be misleading, because again, if you look at this, you're saying, oh, the left-handed test is correct 92% of the time, but it's not. it's actually only correct 67% of the time when you look at it in context of the full situation. All right, let's look at another example together. So this says, suppose Walter operates an order filling machine that has an error rate of 0.5%. He installs a new order filling machine that has an error rate that's only 0.1%. The new machine does 80% of the order filling, which implies, of course, that the old machine does 20%. So a customer calls to complain that there's an error in her order, and he blames the old machine. Is he correct in doing so? What is the probability that if an error is made, it is from the old machine? So to analyze a decision like this, we really need to look at the whole picture. So there's a few common mistakes people might just jump to. They might say, hey, well, the old machine has a higher error rate, so yeah, it must be the old machine that made it, or the probability is that the old machine made it. Or maybe you kind of go the other direction. You say, well, the old machine is only doing 20% of the orders, and the new machine's doing much more of the orders, so it must be the new machine. There's a much higher probability that the new machine is doing it. But you can't just look at these two percentages or these two percentages. You have to look at them as a whole, and you have to look at some different conditional probabilities. So for something like this, we're going to want to make what's called a tree diagram. And here we kind of look at the different layers of what's happening to get to the outcome. So the first layer of this tree diagram could be which machine is doing the order filling. So we know that there's two machines. There's the old machine, and there's the new machine. And the probability that the old machine is the one that is doing it is 0.20, and the probability that the new machine is filling the order is 0.80. But again, we can't just look at those in those individual probabilities because there's another layer of things that's happening. So for each individual machine, two things could happen. They could make an error, or they could have no error. So this is error, and there could be no error. And that's for both the old and the new. And no error. Okay, so let's first look at the probability for the old machine. So if it is the old machine, so the condition is that it's the old machine, we know that the probability that it makes an error is 0.5%, which would be 0.005 written as a decimal. And given that it's the old machine, that means the probability that it does not make an error is 0.995. And then if you look at the new machine, again, the error rate is 0.1%, so 0.001, and that makes this 0.999. But again, these are the probabilities, these are the conditional probabilities, the probability that there's an error given that it's the old, or the probability that's error given that it's the new. But we would like to know the probability that it's old and makes an error, or it's old and it makes no error. And to find those, we're actually going to multiply the two individual probabilities. So for this one, we could do 0.2 times 0.05, and we would get 0.001. So the probability that it is old and makes an error is 0.001. And then to find this probability that it's old and makes no error, we multiply 0.2 times 0.995, and we get 0.199. Then to find the probability that it's a new machine and makes an error, we multiply the two individual probabilities, and we get 0.0008. And then same thing for the last one, multiply those two individual probabilities, and you get 0.7992. Okay, so now let's go back to what they're asking. Again, the customer calls and complains that there is an error. So we know for a fact that there is an error, so I'm going to call this our condition. The condition is that there is an error, so I'll highlight those cases here and here. He blames the old machine. Is he correct in doing so? So what is the probability that if an error is made, again, that's the condition, it is from the old machine? So we're saying what's the probability that it was this path that was taken? So we're finding essentially the probability of old and error given the probability, or given that there was an error. So to do this, our denominator is going to be the probability of error. So we're going to add up these two individual probabilities. So 0.001 plus 0.0008. And then to find this probability, again, that it was old and it made an error, we would multiply these two, which we already did right here. So it's simply 0.001. So this gives us about 0.56. So there's a 56% chance that if an error was made, it was in fact made by the old machine. So again, I wouldn't necessarily say that this is a super accurate statement to make because it's just over 50%. So I would say that he probably should not be blaming the old machine. I mean, it's very possible that it is the old machine, but again, a 56% chance doesn't instill much certainty. All right, I have one last one for you to try on your own. So please give it a shot and hit play when you're ready to check your work. All right, so let's look at this new scenario. Again, the thing that has changed was kind of the split of the workload. So now the old has 30% of the orders and the new has 70%. So you can see when we do that, if you find the probability that it's old and makes an error and new and makes an error, and you add those up, it's 0.22% now. So it is a little bit higher than in the last example. And to find the probability that if an error was made, that it was made by the old machine. So remember, we do the probability of the total of making an error. So you add up these two. And then the numerator is the probability that it is old and an error. And we got that by multiplying these two individual probabilities. So then here we get a 68% chance. So in this case, it's a little bit more likely that it was in fact from the old machine. But again, the overall probability of getting an error increased by a little bit, but not a whole lot. So again, here you could be a little bit more certain that it was probably the old machine, but you know, it's still less than 70% chance. So you can't really be that certain about it. Okay, that is all for today's video. Thank you so much for watching.